Hi guys, so in the last video we discussed how substrate concentration helps in the or affects the enzyme activity, right? So in real time, if it is plotted, that is, if we plot how substrate concentration affects the rate of reaction or the velocity of the reaction, we see that with increase in substrate concentration, the rate of reaction will increase, but only up to a certain point, which is your saturation point, right? Beyond that, which is the max velocity that can be reached, the reaction is not going to get affected by increase in substrate concentration. This particular Vmax, the half of it is known as half Vmax. And the substrate concentration at which any reaction reaches half Vmax is known as its Michaelis Menten constant. Okay, so Km is the substrate concentration at which any enzymatic reaction will reach half of the maximum velocity. When we derive down further from this plot, we get an equation which says V is equal to Vmax into S upon Km plus S. What it gives us is that for any given enzyme, if you know its Km and if you know its Vmax, you will be able to say at which substrate concentration it will reach what amount of velocity. Okay, so in that case, if these two, because these two are constants for any given enzyme, in that case you can easily determine the substrate concentration and its relationship with the velocity. When this particular curve is studied, it's usually studied in the form of its reciprocal curve, which is a linear plot, right? It's called the Lineweaver-Burke plot. When you do the Lineweaver plot, you basically plot 1 upon V and 1 upon S, which makes the curve linear, and therefore it's easier to study. It is extensively studied to understand inhibition. Now, in enzymes, you have three basic kinds of inhibition. You have competitive, uncompetitive, and non-competitive inhibitions. In competitive inhibition, the enzyme normally binds with the substrate, forms the product, right? But in this case, the inhibitor competes with the substrate, as the name suggests, for the enzyme's active site. And therefore, in this case, when we plot a Lineweaver-Burke curve, the Km gets increased. So the substrate concentration at which half the velocity, maximum velocity, can be reached, so you will need more substrate, right? Because why? Because obviously the substrate concentration at which initially all the active sites of the enzyme could be filled, half of the active sites could be filled, is not enough, because most of the enzymes are also getting taken up by the inhibitor. So you need more substrate, and therefore the Km will increase. Okay. In non-competitive, it does not compete. It does not need to compete, because it can already bind to the enzyme's active site, and if not that, it can also bind to the enzyme substrate complex, right? So when it can do both, in both these cases, you don't get a product. So if it is binding to the enzyme or binding to the enzyme substrate complex, you don't get a product. So in this case, even though the substrate concentration at which Km can be reached, so half Vmax ka substrate concentration, will stay the same, the Vmax will fall. Obviously, the reaction will become much prolonged. So the maximum velocity it can reach will become much lower. Okay. In uncompetitive inhibition, what happens is that unless and until the enzyme has bound to the substrate, the inhibitor can't bind. Okay, so you have to have the enzyme's active site filled with the substrate for the inhibitor to work. And therefore, in this case, both the Km as well as the Vmax is reduced. As far as questions are considered, in boards, you usually get asked about Km and this curve, but the whole of the everything else, the competitions, Lineweaver-Burke plot, you are not asked for derivations or sums, but you can be asked equations. You can be asked to identify the kind of competition from the graph, or you can be directly asked what happens to the Km and the Vmax when different types of inhibitors work on the enzyme. I hope this was clear enough. We will continue in the next video. Thank you.